Hello everybody and welcome to page 149 of the workbook. This is the beginning of section 6.3, the very last section of our course. Yay! So we are going to talk about the adjoint of a linear operator here, and that's going to lead us to a formula for the least squares method that you might remember from statistics. Okay, so this process all starts out with something called the adjoint theorem. Let's read this together. So we're going to start with an n by m matrix with entries in the complex numbers. Okay, we're going to be talking about the standard m and n tuples of complex numbers and just be using the standard inner product in this discussion, the standard dot product for complex numbers. Okay, and it turns out that there's kind of an interesting relationship, an interesting equality that involves inner products that turns out to be true. The inner product of ax with y is equal to the inner product of x with a star y, where a star is the matrix that we call the conjugate transpose, also known as the adjoint. Remember, I think we mentioned that matrix very briefly back in section 6.1. It was basically the matrix that you get from A by doing two things. You transpose A, and you take the complex conjugate of every entry in A. Okay, so let's see if we can prove this theorem. This is going to lead us to the least squares formula eventually. All right, so let's make a couple of remarks first here. Okay, throughout this proof, we're going to view vectors in CK as column vectors, just because that's convenient for what we're doing here. Okay, and we're going to start by just choosing a couple of arbitrary vectors here. Okay, I'm going to call them A and B. So A is going to be the vector that looks like A1, A2, up to AK transposed, and B, similarly, B1 up to BK transpose. Okay, and we're about to write down a formula, but I want to make a comment before we do. Notice that those two vectors, A and B, are column vectors, okay, because we wrote them as rows, but we put a transpose on both of them. That takes those rows and turns them into columns, so keep that in mind as we go through this proof here. Okay, so with that designation of A and B, we have the following. We're going to take and matrix multiply B star times A. Okay, what is B star? Well, that's the conjugate transpose of B. So B started out as a column, so we're going to transpose it into a row and take the complex conjugate of every entry. It's going to wind up looking like this. A, on the other hand, is a column vector. It's going to stay the same, so we're taking that row vector and multiplying it by a column vector that looks like this. And the question is, what do we get if we do that? Okay, well, let's examine the size of our matrices here. So the matrix on the left, that has one row and k columns. We're multiplying that by a matrix that has k rows and one column. What's the size of the product going to be? It's going to be a 1 by 1 matrix, but a 1 by 1 matrix is just a scalar. Okay, and if we write that scalar out, here's what it's going to look like. We're just going to get a bunch of products added together. And my question to you is, do you recognize that expression that we came up with here? That's just the standard inner product of A with B. Okay, so we've just discovered kind of an interesting way of writing the standard inner product in terms of matrix multiplication, a row matrix times a column matrix. All right, so file that fact away. We're going to come back and use it a couple of times. Okay, so here's what we have as a result of that. Okay, we are going to start with the inner product of x with a star y, and I'm going to point out that that's the right-hand side. Back up here at the top of the page of what we're trying to prove, we're going to try to show that that's equal to the left-hand side. Okay, and our first observation is going to be to use equation 1 that we have here. We can rewrite that inner product, if we think of the x as our a and the a star y as our b, Formula 1 allows us to rewrite that as b star a. Okay, and if we do that, here's what it would look like. Here's the b star, and we're going to multiply that by a. Okay, so this came from Formula 1 above. Okay, then we're going to use a couple of properties of conjugate transposes. Okay, so for example, I claim that this part underlined here we can rewrite as y star times a star star. Where did that come from? Okay, well, that comes from the fact that for any two matrices, if you take the conjugate transpose of a product, you get the product of the conjugate transposes in the other order. I'll leave it to you to verify that fact. Okay, and then as you might guess, if you take the conjugate transpose of a matrix twice, you're going to just get back to the matrix again. So this is really y star a x. Okay, since a star star is just a. Okay, and we're talking about matrix multiplication here, which is associative, so we can regroup this, okay, as follows. And then we make the observation that that last line is really the inner product of ax with y, again by equation 1. This time, we're using equation 1 with ax equal to a and y equal to b. You can check that that last equality is true. Okay, and notice where we started and where we stopped. Those were the two things that we wanted to show were equal, and so we are done.